galvanic cells. Galvanic cell is an electrochemical cell. It converts the chemical energy of spontaneous redox reactions. Generally speaking, chemical energy into electrical energy. And when we say chemical energy, this is obtained from spontaneous redox reaction. Redox reaction means oxidation and reduction together, and spontaneous means naturally, automatically. So we are able to get chemical energy from this spontaneous redox reaction that is taking place in the electrolyte, and usually oxidation occurs at anode and reduction occurs at cathode. And this energy, chemical energy, is converted into electrical energy or electrical work. After all, capacity to do your work is energy, is it not? So this kind of electrical work may be used for running a motor or any other electrical gadgets like water heater, fan, geyser, etc. Let me consider a Daniel cell where we have the zinc electrode and copper electrode. Let me represent the Daniel cell in two electrolytic baths like this. And this is an electrolytic bath. These are two electrolytic baths. One is containing a salt of zinc solution containing some zinc salt. Another is copper salt. So in zinc electrolytic bath we have zinc electrode kept in zinc salt, that is, it is represented by Zn plus. And here copper salt may be copper sulfate, so Cu 2 plus, and this is zinc 2 plus, so aqueous. Sorry, this is, of course, this is copper and copper 2 plus. It should be represented as Aq. Okay. So we have here zinc electrode and copper electrode. This is zinc, this is copper electrode. And these two are connected through a galvanometer, so that current passing through this can be measured or monitored. So the current is, the electrical energy is obtained here by dipping these two electrodes in the respective electrolyte. That is, this may be zinc sulfate solution. This is copper sulfate solution. And this can be represented as zinc electrode dipped in zinc sulfate solution, and this can be represented as copper dipped in copper sulfate solution, aqueous solution. And this can also be represented as ion also, zinc dipped in zinc 2 plus ion, you can put aqueous. And similarly copper dipped in copper 2 plus ion, like that. So by dipping this we are able to get some current, and more interestingly, we cannot just like that get the current without introducing this salt bridge. So this is called salt bridge. It's a kind of U-tube arrangement where we kept the agar salt, KCl in agar-agar solution. So this is called salt bridge. And this is the zinc 2 plus and with negative electrode, and this is positive electrode. Okay. In fact, we can represent this by, as I already mentioned, zinc, and this is as solid by zinc 2 plus, and this is aqueous solution. Okay. Similarly, we can have this represents the salt bridge. And this is copper 2 plus slash copper. Okay. Here the left electrode is zinc, the right electrode is copper. Okay. Because at the zinc oxidation takes place. Zinc 2 plus plus 2E. So this can be declared as anode. So oxidation, because removal of electron. And at cathode, Cu 2 plus plus 2E gives reduction occurs, that is copper occurs here. Okay, this is solid, this is solid, this is aqueous, this is aqueous. Right? Now we can combine these two. Okay, let us combine these two, and this is zinc solid plus these two electrons can be cancelled since they are in the opposite sides. and zinc here, copper 2 plus ion, aqueous ion, gas zinc 2 plus aqueous, and then copper solid. Okay, this is called the cell reaction, and these two are called the half cell reactions. By combining these two, we are able to get the cell reaction, right? And when we want to find out the EMF of the cell, we can put E right minus E left. That is the simple formula. So what is the cell EMF? And that is when I put naught at the top, that is at the superscript, that represents the standard state. So the cell EMF, that is standard cell EMF of this Daniell cell, this is called Daniell cell, is given by E right standard cell potential, this is the electrode potential, minus the electrode potential of left electrode. Okay, so in order to distinguish the cell EMF from the electrode potential, let me use this convention so that it will be better for you. Okay, minus, what is this? Electrode, standard electrode potential of right electrode, minus standard electrode potential of left electrode, results E naught, the cell EMF. Okay, so E or standard electrode potential, right electrode potential, and this is standard left electrode potential. Okay, and we have certain set of standard values. Probably this will be given, or you have to refer the reference tables, electrochemical series. So here you have got the value of the right electrode, standard electrode potential of right electrode is equal to 0.34 volt. And standard left electrode potential is minus 0.76 volt. So usually this represents, these two represents by our Indian convention reduction potential. Take down. You can interpret either in terms of oxidation potential or in terms of reduction potential. Let me consider as per the Indian convention reduction potential. In the electrochemical series, these reduction potential are cleanly arranged either in ascending or descending manner. Okay, at standard states. So when you got certain values, assuming that this is the standard hydrogen electrode potential, that is E She, standard hydrogen electrode potential is 0, and if you got minus value, and you will get plus value in the top. So when it is a positive, then the reduction is so natural. When it is negative, it is understood that is the electrode may undergo oxidation, because it is negative reduction potential means it may be an oxidation one. it will undergo oxidation. And based on these values, for example, and what is kept in the right, on the right we have got copper. So copper has undergone what? Reduction. Are you able to follow? So its reduction potential is clearly mentioned here as a positive one. And since the zinc undergoes oxidation, its reduction potential is negative. So when I say negative reduction potential, which is nothing but positive oxidation potential. Is it clear? Now what is the oxidation potential of copper? You can say minus 0.34. And what is the oxidation potential of this one? What is that? Copper, zinc. Just you have to say the reverse. Okay. So, but this should not be confused with the positive and negative. So we have to maintain either reduction potential or oxidation potential. So as I already mentioned, as per Indian standards, we maintain only reduction potential. So you have to consider only reduction potential in this case. Is it clear now? Right. So when I say reduction potential is negative, then you can very well understand that that particular electrode undergoes oxidation. Is it clear? It has more tendency for an oxidation reaction. So in such a way, that is, we can choose the electrode also, whether we have to put it on the right or left. And by convention, that is always left on the, oxidation, that is anode on the left side, cathode on the right side. Okay. So anode on the left side, right? Cathode on the right side. Correct? Okay, so this is the way we have to maintain. Are you able to follow? When cell reaction is taking place. But when we are getting some energy from that, it will be reversed. Okay, so let there be no confusion at all. Right. Now, in this case, now we are going to have the value of this one. This cell, the Daniell cell, what could be the value? So we can calculate E naught cell is equal to what is kept on the right side? Copper. On the right side we have got copper. On the left side we have zinc. So right is 0.34. So you can put on the right side what we have kept? Copper. And the copper reduction potential should be represented as copper 2 first and then followed by copper. So this is the way we have to represent the reduction potential. Are you able to follow? And what about this? Here minus, okay. What is this? What is the reduction potential of zinc? Zinc 2 plus by zinc. Okay. But probably in this case we have reversed. So usually an electrode is represented by the electrode first followed by the electrolyte. So let us follow the same convention instead of putting, even though it is reduction potential, but let us remember that an electrode should be represented by the metal followed by the metal solution. So in that case, let us not proceed with this. Instead, let us go like this. E naught cell is equal to electrode potential copper dipped in copper 2 plus, that's all. Okay. But when it is represented in the cell notation, that is different. See this copper 2 plus in copper because it's reduction, whereas this is oxidation. So you should remember this. So minus, so I think there is no confusion here. Okay, right. So E naught because standard state. Okay, and you can put zinc. So hereafter you can simply put zinc bar zinc 2 plus for our convenience. Okay, and this is AQ. This is understood. We need not put every time like this. And this is solid electrode. Okay, because we have got some gaseous electrode also. So we may have to mention initially. Later you need not. Now we have got the value So what is the value of the copper potential? That is 0.34, is it not, volt, minus of minus 0.76 volt. So therefore 0.34 plus 0.76, so it is equal to 6 plus 4, 10, balance 1, 8, 3, so 1.1. So the Daniel cell value is 1.1 volt. Are you able to follow this? It means what? When you keep this copper and zinc electrodes, you are able to get this current 1.1 volt. Okay, such a potential can be obtained from Daniel cell. Is it clear? Now, remember, let me further explain on this Daniel cell. So here, let me go back here. So what happens here? That is, as I already suggested, the zinc, okay, the zinc solution is here becoming zinc, okay, so where in fact the electrons are moving from here to here, okay, when we are able to get some current from this. But let me initiate the potential in such a way, okay. Now listen. So I am now explaining about the Daniel cell electrodes in the respective salts. So we have two electrolytic baths, and here salt bridges there, and we have the zinc electrode, copper electrode. So we have got the solution here, the respective solution. Let me say this is zinc and this is copper. So zinc sulfate, copper sulfate solution. Zinc rod is dipped in zinc sulfate, copper rod is dipped in copper sulfate solution, and these two are interconnected by the salt bridge. Okay. Now I am connecting this through a voltmeter, and let me connect here to a rheostat like this. This is the rheostat. This is the jockey arrangement where we can fix the various resistance also, and thereby you can change the potential. And let me give the negative potential here and positive potential for the electrode like this. And let me say the external EMF is less than 1.1 volt. Let me say like this. Okay, less than 1 volt, 1.1 volt. Now when E external is less than 1.1 volt, what happens actually? Electrons flow from zinc rod to copper rod. Okay, zinc rod is here and copper rod is here. So the electrons are moving in this way. These are all electron. Okay, but what about the current? Current in the opposite direction. Let me represent by I. Usually the direction of current is opposite to the direction of electron, running of electron. And now, so this is zinc and it is indicated as anodic even though it is minus. So this is the important point you have to remember. You may wonder, sir, anode is positive, is it not? But in this case it's different. Okay, and copper, so here, okay, so this is anode, this is cathode. Right? So the electrons flow from zinc rod. The electrons flow from zinc rod to copper rod. And it means what? Current flows from opposite copper rod to zinc, right? And then zinc dissolves at cathode. Zinc dissolves at cathode. Zinc dissolves at anode. Sorry, anode. Okay, and the copper is deposited. So copper deposits at cathode. Are you able to follow? Now let us take the next case. What am I doing is I am keeping the external voltage equal to 1.1, right? So again the same setup. So this is the electrolytic bath. So you have zinc sulfate bath, copper sulfate bath, and they are interconnected by the salt bridge. You are keeping two electrodes. One is a zinc electrode, another is copper electrode. They are connected through the galvanometer like this, or voltmeter, in order to measure the voltage. Voltmeter, here also voltmeter. And we are taking a jockey like this and keep it on the rheostat like this, and thereby we can change the potential. And here I am giving negative terminal and here positive terminal. Okay, this is negative, this is positive. And here the E external is exactly equal to 1 volt, and that's what we have derived, is it not? So in that case, now these two are balanced, and therefore there is no current flowing. Got it? no current flows. Okay, take down. So when E external is equal to 1.1 volt, what happens? Now, no flow of electrons, right? And no current flows. Then it means no chemical reaction, because they are counterbalanced, right? Here zinc dissolves at anode. So when it is dissolved at anode means what? It is converting into zinc 2 plus, and that is why it is getting corroded or dissolved, whereas copper is getting deposited. So Cu 2 plus plus E 2E gives Cu. So in this case, how the reaction is occurring? Zinc dissolves means that is zinc undergoes oxidation. Are able to follow? And that's why it's getting into the solution. From the metal to metal solution, it is getting dissolved. So this undergoes oxidation. Whereas in this case, copper is deposited means at cathode, Cu2 plus 2 electron combine to form Cu. Are able to follow? And that is why we say copper deposited at the other electrode. Okay. Is it clear now? Right. Next one. Now let us proceed with the external potential, that is applied potential here, above 1.1 volt. Now let us study the situation. Okay. So it means I am reversing the potential. Do you understand this? Are you able to see this? So I have changed the potential. See, this is plus and this is minus. Got it? In the previous case I kept minus on the left and plus on the right. Now I have changed, and this is connected to the jockey, and we have now current on the other side. It is getting deflected like this. Okay. Now it is connected. I think whether I have connected here. Yes. Right. And let me bring the electrodes here. So I have dipped between two bars, and this is zinc and this is copper. Now here the cathode. Okay, so this acts as cathode. So this is plus positive and this is minus, right? So this acts as cathode and this acts as anode. Okay. Now the electrons will be moving from in this way externally, and the current will be in the opposite direction. This is current. Okay. Now what is the condition here? And you have got the electrolytic bath as usual. We have got zinc sulfate here and copper sulfate solution. Now what about the potential? The E external potential, external EMF is increasing, so it is above 1.1 volt. So in that case what happens? So when the external applied voltage is increasing, that is greater than 1.1 volt, what happens? Electrons flow from copper to zinc. Am I right? Copper to zinc, correct? Look at the diagram, copper to zinc. And what about current flow direction from zinc to copper? Okay, now here when zinc is deposited, at zinc electrode. Okay, and what about copper? Copper dissolves at copper electrode because we are getting energy from that. Are you able to follow?